Hello everybody, I hope you're all doing well. So I want to solve a short problem that will act as a review for dynamics, and this will be useful as we proceed further in ME 3260. And towards that I'm showing you the following problem. In this problem I have a disk of radius little r. Okay, so this is a disk of radius little r. And let's say that the mass moment of inertia of this disk is given to us as mr square by 2, or we can essentially just call it as Ig. Okay, so the mass moment of inertia of the disk about its center of mass, which I'm going to call as capital G, as you can see in the figure. Okay, so this is given to us as I suffix G is mr square divided by 2. Okay, so I'm assuming that this is a solid circular disk. Okay, and the mass of this disk is obviously little m. All right. Now, what's going on in this problem is that this disk, which was initially at time t is equal to 0, you can see it is sitting at a location. This is traveling around a fixed large circular track. Okay, so the disk travels around a large circular track of radius capital R. Okay, so this track is a circular track of radius r, and it's also a fixed track. And most importantly, at any point of contact between the disk and the track, we are going to assume that the disk is rolling without slip. Okay, so the disk, we are going to assume that the disk rolls without slip relative to the fixed track. All right. And you essentially see the story depicted in this figure here. Initially, the disk was at time t is equal to 0. The disk was sitting at the top of the fixed track. And then after some time, perhaps somebody has nudged this disk a little bit by giving it some initial conditions. And it's been displaced. And the disk is traveling along or rolling along the track. And you're looking at some other arbitrary time, little t. Okay, you see that the point C is the point of contact between the disk and the track. Okay, so in this figure you can see point C right there. I'm going to mark that here. So that's point C right there, and that's the point of contact between the disk and the track. Okay, so I'm going to write that down. So point C is the contact point between the disk and the track at some time instant little t. Okay, and importantly, you're told that this disk is rolling without slip, which means that at any point in time, the relative velocity between the point of contact and the track, and I'm trying to draw a straight line, which it doesn't let me do for some weird reason. Yeah, there you go. So the relative velocity between the point of contact and the disk is taken to be 0, and the relative acceleration in the tangential direction is going to be 0 as well. And we're going to talk about this as we solve the problem further. Okay, what are we supposed to do? We are supposed to obtain the equation of motion for the disk. Okay, so obtain the equation of motion of the disk. All right. Now we are essentially looking at the following figure, and if I just go back to the figure, I have this position at time t is equal to 0. I have the position of the disk at time t is equal to some t, arbitrary t. The point O is a fixed point. Okay, so this is the center of the circular track. So this point O is a fixed point. And perhaps you might have come across problems like this in your dynamics lecture. If not, we will solve this step by step. Okay, so I'm going to assume that as time goes from 0 to some arbitrary time instant t, the angle that is swept by this line OG is going to be theta of t. Okay, so I'm going to say that this angle here is going to be theta of t. Okay, so I'm going to take this figure and we're going to start setting up a coordinate frame that will help us describe the kinematics of the problem in terms of the velocity, the acceleration, and the angular velocity of the disk. And then we will later on go into the kinetics of the problem as well. Okay, so I'm going to copy this figure and let's see if we need everything or just a few of these things. Okay, so my aim is to look at it at some arbitrary time t. That's when the equations of motion will be obtained. So the solution. In the solution, typically I will set up a coordinate frame. Suitable coordinate frame. Okay, then we will look at the kinematics of the problem. And the last thing is we will look at the kinetics of the problem. Okay, so these are the three things that we are going to be doing. All right. So with that said, I'm going to basically paste the figure that I had from previously. I'm going to get rid of some of these things. We obviously know that this is the situation at some time t, so I'm not going to belabor that point. This is a fixed point, so maybe let me just keep it that way. All right. First things first, I'm going to set up a coordinate frame. This coordinate frame, I have to set up what is called as an inertial coordinate frame, or a fixed coordinate frame, or a fixed reference frame. This is set up at the point O. Okay, so I'm going to choose the horizontal as the I direction, the I hat unit vector direction. Then I'm going to choose the vertical direction as the J hat unit vector, and then the direction that's going to be coming out of the page. I'm going to scuttle down all these points, and we know this by now. The direction that's the unit vector that's going to come out of the page is going to depict the k unit vector, okay, or the k hat unit vector. Okay, so this is going to be out of the page. And the basic idea is that if you use a right hand rule, if I go from I to J and if I cross the fingers of my right hand and I curl it around, the direction of my thumb is given by the k unit vector. Okay, so we essentially say that this is I crossed with J is equal to k. Okay, and this can be expressed in the form of a triad, which you may have come across in dynamics. This same information can be written as I hat, J hat, K hat, and then I draw these circular arrows here, which essentially tells me the following. If I do I cross J, I get K. So this tells me that if I do I cross J, this gives me K. If I do J cross K, it gives me I. And if I do K cross I, it gives me J. But watch out, if I go from J to I, you see this is essentially going against the grain of the triad, because I'm saying that if I'm going from I to J, it's positive, and this is basically the right hand rule once again. But if I go from J to I, this is going to give me minus K, because I'm going against the grain. Okay, and so on. Okay, so this is essentially the triad, and I, J, and K are the unit vectors of a fixed reference frame. So I hat, J hat, and K hat, these are the unit vectors of a fixed reference frame, reference or coordinate frame. At point O, which itself is a fixed point. If point O is fixed, it means that its velocity and accelerations are all zero. Okay, such a point is also called as a stationary observer. Okay, so this is also called as a stationary observer. And usually when you do a problem in dynamics, you always want to set up a stationary observer, set up a fixed coordinate frame at a stationary observer so that you observe the events of the problem unfurling with respect to this particular stationary person or stationary observer. Okay, so this is the first thing we do. The second thing I'm going to do in this problem is I'm going to set up a coordinate frame which is kind of showing how the center of mass is moving. Okay, and you can obviously see that the center of mass is traveling along a circular path as the disk is rolling along the fixed track. And so typically a circular path implies that I'm going to have some kind of a curvilinear coordinate system. And most of the times I typically tend to like the tangential and the normal unit vector system. You're free to choose the radial and the transverse coordinates as well. They're all going to give you the same information no matter how you solve the problem. Okay, one way versus the other does not change the final result of the problem. All right. So I'm going to set up a coordinate frame. So the tangential direction, as you can see, this is going to be tangential to the circular path that the center of mass is taking. So I'm going to call this unit vector as E suffix t, as you do from dynamics. And then the vector that is pointing, the unit vector that is pointing towards the center of rotation is going to be the normal unit vector. And this is going to be E suffix n, which is going to be pointing towards the center of the path O. Okay, and once again I can set up a triad. Now E suffix t and E suffix n are unit vectors that change with time. Okay, so E suffix t, E suffix n are the tangential and the normal unit vectors. They change with time, change position with time. They are not a fixed frame as opposed to the IJK coordinate system, which is a fixed reference frame. Just to maybe make the situation a little more clear, I don't want to confuse people. This K direction is obviously not coincident with the En direction, so I want to make sure that that is also seen here. So this K hat is out of the page. ET and En are on the plane of the paper. Okay, so maybe let me make that point as well. So ET and En are on the plane of the paper. Okay, and then I can immediately recognize that if I have two unit vectors on the plane of the paper, if I take the cross product between the two, I get the third one. Okay, so if I use a right hand rule, if I go from ET and twirl it all the way to En, you can see that if I use a right hand rule, the fingers of my right hand aligned with the vector ET, and I am swinging my arms all the way to the En unit vector, my thumb is going to be pointing into the page, which means that the cross product of ET and En is going to give me minus K. Okay, because the vector that is pointing into the page is negative K. Okay, so once again, if I look at ET and En, ET crossed with En is going to give me negative K. Okay, so ET crossed with En, this problem is going to give me negative K. Okay, so this is going to be into the plane of the paper or into the page. Okay, so which means I can set up a triad here. So this is called as a triad, and I had a triad drawn previously as well, which was this creature here. So this is called as a triad as well. Triad meaning three unit vectors. That's about it. Okay, three unit vectors that are mutually perpendicular to each other, so they form an orthonormal basis. All right, so in this case the triad is going to be ET first, then I'm going to write En, and then the third vector of the triad is minus K, because if I go from ET and I cross it with En, I get negative K. This is the positive convention, so ET crossed with En is minus K hat. And then if I do minus K hat crossed with ET, this is going to give me En. If I do En crossed with minus K hat, this is going to give me ET, and so on. Okay, or if I do En crossed with ET, look at this, En crossed with ET is going to give me minus of minus k hat, or it's going to give me essentially k hat. Okay, fantastic, right? So this is the triad that I'm looking at. So these are the two things that we are setting up: a fixed coordinate frame and a moving observer. Okay, and then based upon these, we're just going to start doing the kinematics of the problem at this point in time. All right, so I'm going to go ahead and look back on my figure here with all the coordinate frames set up. Okay, so look at this. I'm going to take all of these guys and then bring it down below. Hopefully that copied everything out. Okay, and I guess not. All right, so I'm going to copy all of this and hopefully paste it here. All right, fantastic. So I have my triad. I'm just going to write the triad out. So this is going to be ET En minus K. This is usually how I solve problems in dynamics. I have my triad all the time. Okay, I, J, and then K. And this is essentially looking at it as if it's a clock. If I go from ET, I cross with En, I get minus K. If I go against the grain, it means that I'm going to have a negative sign. So minus K crossed with En is going to give me minus ET. Okay, for example. Okay, so these are my triad. This is a triad that changes with time. So this is not a fixed system. Okay, this is a fixed triad. A triad is a set of three mutually perpendicular unit vectors. Okay, so triad is a set of three mutually perpendicular unit vectors, which means that they form an orthonormal basis. Not very important as to where we're going to be using that particular scenario, but I just want to let you know about it. Okay, so radius of the disk is little r, radius of the big track is capital R. Now I'm going to start writing out the velocity of the point G relative to the point O. Okay, so velocity of point G relative to the point O. So this is the velocity of point G relative to the point O. Because the disk is traveling along a circular path, the velocity of point G relative to the point O is going to be in the tangential direction. And this is going to be the total length from the point O to the point G multiplied by the rate of change of the angle theta. Okay, so since circular motion, point G performs circular motion about the point O. Okay, so which means that the velocity of G with respect to O is going to be the length of the track plus the radius of the disk and times theta dot, and this is going to be in the tangential direction, as you can very well guess. Okay, so once again, you look at the track, you look at the center of mass, it's rotating along a circular path. The radius of that path is little r plus capital R, and obviously the rate of change of the angle is theta dot, and so this is the velocity of the center of mass. I can also write the acceleration of the center of mass. Okay, so the acceleration of the center of mass. So this is the velocity. I just want to underline this. Okay, once again, I'll be going a little slow on these problems because this acts as a review for a lot of us. So acceleration of G slash O is the acceleration of G relative to the point O. Okay, the acceleration of point O is 0, so typically these are accelerations with respect to a fixed reference point. Okay, that's how typically I write it out. And so since the path is circular, okay, so since G performs circular motion about O, the acceleration of G slash O is going to have something in the tangential direction, something in the normal direction. This you know from basic dynamics, that the acceleration in the tangential direction is going to be the length of the track, which is going to be r plus little r times theta dot in the tangential direction, and then this is going to be in the normal direction, which is pointing towards the center of rotation. This is going to be r plus r times theta dot square in the normal direction. Okay, so this is the acceleration. All right, so I have the acceleration of g slash o, velocity of g slash o. Now what do I do next? Okay, so this is based on circular motion. Okay, of g relative to the point O. Okay, now what do I do next? What I want to do is I want to understand what the angular velocity of the disk is, okay, in terms of the variables that are given to me. So my aim, obtain the angular velocity of the disk. I'm going to call it as omega d, okay, in terms of little r, small r, and theta as a function of t. Okay, and obviously my aim is also obtain the angular acceleration, which I'm going to call alpha disk, in terms of r, and theta of t. Okay, so this is the angular acceleration of the disk, alpha. This is the angular velocity, omega. Okay, so we have the acceleration of g. I have the velocity of point g, which is a point on the disk, the center of mass of the disk. How do I use this information? Okay, now we are told, so to obtain omega d and alpha d, we use the fact that the disk rolls without slip relative to the fixed track. Okay, so this is the information that we're going to be using, and how to do that, we're going to look at it the following way. I'm going to copy my figure once again. My hope is I already have that done. Oh yeah, beautiful. So I have my figure once again. Okay, so I'm looking at this point in time. I'm going to get rid of all of these guys. That was the initial position of point G. Okay, I'm not interested in that. So this was G at time t is equal to 0. This is now the new location of G. So look at this. For a body that rolls without slip, okay, so for disk rolling without slip, what are the things that have to be satisfied? The constraint. So this is essentially a constraint that has to be satisfied, and because of the fact that the disk is rolling without slip, you would know from dynamics that the force of friction is actually the static friction force. The static friction force is a constraint on the body, as opposed to the kinetic friction force, which is essentially treated as an external force. Okay, so for disk rolling without slip, here is the fact. Okay, the relative velocity at the contact is 0. And the second thing is the relative acceleration at the contact point but in the tangential direction only, is equal to 0. If the entire acceleration vector is 0 and if the entire relative velocity vector is also 0, then it means that that point is a fixed point. Only a fixed point, a point that is forever fixed in time, can have both the velocity and the acceleration equal to 0. When a point is rolling without slip, when a body is rolling without slip with respect to some other body, the velocity vector is 0 at the contact point because there is no relative sliding between the body. Okay, so no relative sliding, but the tangential component of the acceleration is 0. The normal component of the acceleration is not 0 because that point has to peel off so that the next point on the disk will come to contact as time proceeds further. Okay, so this implies that the normal component of the acceleration of relative acceleration is not 0, so that the contact point can peel off the surface and let the next point on the disk come into contact at the next time instant. Okay, so this is a very important piece of information. We may or may not use this in this particular problem because my aim is to maybe simplify it and then give you the presentation of the problem quickly. Okay, so the normal component of the relative acceleration vector is not 0. This is because the contact point has to actually peel off of the surface so that the next point comes into contact, because this is a dynamic system. The disk has to, for heaven's sake, it has to keep rolling on the surface, right? If the acceleration is 0 and if the velocity is also 0, the disk is just going to sit fixed on the surface. This is going to be a problem in static equilibrium, which is not what we are dealing with here. Okay. All right. So we move on. So what I'm going to say is that the velocity of the point C, which is the point of contact, with respect to the fixed track is 0. Okay, so the relative velocity of point C, so C is the contact point, as you can see. Okay, so this implies that the contact point, so velocity of point C relative to the fixed track is 0, or if I say velocity of point C relative to the track is 0, this essentially means that velocity of point C relative to a fixed point O minus, if I call, so C is a point on the disk. Okay, so I'm essentially saying that C is a point on the disk, point on disk contacting the track, and let me say that D is a point on the track contacting the disk. Okay, so if I go ahead and say that here, so let's call this point as the point D. Okay, so C is a point on the disk, D is a point on the track. At that instant in time, the relative velocity between C and D is 0. Okay, so this essentially means that the velocity of C with respect to a fixed observer minus the velocity of D with respect to a fixed observer is 0. Okay, D is a point on a fixed track. Which essentially means that velocity of D relative to O is 0, because it's going to be a point on a fixed surface. Its velocity is 0, which implies that velocity of C is equal to velocity of D slash O, which I obtained from this particular equation here. This is equal to 0, which means that velocity of C slash O is also 0 at that instant. This is very important. It's not as if the point C has a velocity that is permanently 0, or any contact point is permanently 0 at all instances in time. The next instant in time, some other point is going to come in contact. That point will have a 0 velocity. Okay, at a different location on the track. All right, this point C at the next instant has moved to some other position on the disk, so its velocity is non-zero at some other instant in time. A new contact point is going to come into place. Okay, so this is essentially what I'm saying here. So watch this. So now use the velocity equation from dynamics to relate velocity of the center of mass of the disk and the contact point C. Okay, so this is done by making use of the angular velocity of the disk. You may recall from dynamics, okay, if I have 2 points on the same body, okay, let's call them as points A and B on the same rigid body. Okay, then we know velocity of A with respect to some fixed observer is velocity of B with respect to some fixed observer plus omega of the body crossed with the position vector from the point B to the point A. Okay, so I'm going to call it as R A slash B. So here O is a fixed point. Okay, and R A slash B is the position vector drawn from B to A. Okay, so this is based on undergraduate dynamics. You would have come across this equation when you look at rigid bodies. Okay, so we're going to use that equation to relate the velocity of point G to the point C. Okay, and I'm going to see if I can do it in this page, or probably maybe I'm going to go to the next page and then do that. And maybe in the meantime, let me also copy this figure and see if I can maybe do it here. Yeah, I think I can probably do it here. Okay, all right, so all we are doing is the kinematics. Okay, so I can say that velocity, so relate the velocity of G and C, and I'm going to say that the disk is rotating with an angular velocity omega disk drawn this way and an angular acceleration alpha disk drawn this way. I'm just assuming it. Okay, so assume. I don't know at this point in time if this is right or not. Omega of the disk is some unknown magnitude and in the k hat direction. It's rotating clockwise. Okay, so this is unknown. Okay, and then alpha of the disk, I'm going to assume that this is minus alpha disk in the k hat direction. Okay, so this is an assumption. I really don't know if this is clockwise or counterclockwise, but I'm just going to assume it. Okay, once again, this is unknown magnitude. Okay, so this is also an unknown magnitude. Okay, now I'm going to relate the velocity of point G to the point C. So we're going to do this very carefully. So velocity of G relative to a fixed point is velocity of C relative to a fixed point plus omega of the disk crossed with the position vector from the point C to the point G. Okay, we know from before we know that the velocity of C is essentially 0. Velocity of G is going to be R plus R in the theta dot tangential direction. Okay, so this is what we know. And I have assumed that omega of the disk is clockwise. I don't know if this is true or not, so I'm just going to fill in the details. So this essentially tells me that R plus R times theta dot in the ET direction, this is going to be 0 vector. Okay, and then this is minus omega disk k hat cross product with R G slash C. What is R G slash C? I'm sitting at the point C looking at the point G. Okay, so this is the vector R G slash C. If I'm drawing it this way, okay, I'm going to call that as R G slash C. And you immediately notice it is in a negative En direction. Okay, so RG slash C is nothing but the radius of the disk, but in a negative En direction. So if I look at it this way, so this is minus R in the negative En direction. Now I look at my triad. Okay, so I had ET, En, and then minus K. This was my triad from before. Okay, and if I look at it that way, so this is the triad. I'm going to bring my equation from above. So this is R plus R theta dot in the ET direction. This is going to be minus and minus becomes a plus. So this is R times omega of the disk times k hat crossed with En. Okay, now what is k hat crossed with En? If I do minus k hat crossed with En, look at the triad. Minus k hat crossed with En is going to be minus Et, right? Because I'm going against the grain. The positive sign is if I'm doing it clockwise, but k hat minus k hat crossed with En is going to give me minus Et. So which means that minus of minus k hat crossed with En, which is going to be k hat crossed with En, is going to be minus of minus Et, which is going to be Et. So if I do the substitution here, r plus r times theta dot in the Et direction is r times omega d times Et, and which obviously tells me that the two sides have the same unit vectors, which means that their magnitudes have to be the same. So if I do that, then I get omega of the disk is going to be r plus r divided by little r theta dot. Okay, so this is the magnitude. Now there is a quicker way to get alpha of the disk, because omega of the disk is written as a function of time. Alpha of the disk, I can say, is going to be d omega of the disk by dt. So this is just going to be r plus r divided by r times theta double dot. Okay, so this is just a differentiation of theta dot. Okay, so that's theta double dot. The radii are all constant. This is one way of doing it. The other way is to relate the acceleration of point G to that of point C. Okay, I'm going to go maybe very write this very quickly. Maybe if you want to look at the acceleration of C, okay, due to the fact that it rolls without slip, the acceleration of C relative to the point D, which is a point on the track. Okay, so I guess I shouldn't, so this D is the disk here. Okay, so this is the disk. I just want to make a caveat here. Unfortunately, I use the point D to signify something on the track as well. So that point D is a point on the track. Okay, due to the fact that it rolls without slip, the acceleration of C slash D in the tangential direction is equal to 0. Okay, but we essentially know that the total acceleration of point C with respect to some point O is going to be something in the tangential direction and then something in the normal direction. Okay, so this is in general, but point D is a fixed point on the track. Okay, so which essentially means that the acceleration of C with respect to D in the tangential direction is 0. Relative acceleration is nothing but the difference between the absolute acceleration. These are all in the tangential direction is 0. Since D is a fixed point on the track, this acceleration is going to be 0 because it's a fixed point. And so this tells me that the acceleration of C with respect to O in the tangential direction, which is A suffix T, Et, is 0. Doesn't mean that the point C is a fixed point. It still has a normal component of acceleration. So which essentially means that the acceleration of point, I have made a mistake here. This is supposed to be Et. Apologies. Okay, so this means that this creature is out of the equation. Okay, and so one can relate the acceleration of G and C using dynamics background or dynamics equation from before. Okay, so this is essentially acceleration of G slash O with respect to a fixed point is acceleration of C slash O plus alpha of the disk crossed with the position vector from C to G minus omega square of the disk, the scalar omega square of the disk, times the position vector from G to C. Okay, and it will give you the same answer. Acceleration of G slash O is from before was r plus r theta double dot in the Et direction r plus r theta dot square in the en direction from earlier. Okay, acceleration of c slash o is going to be 0 in the tangential direction, and then some unknown value in the normal direction. This is due to roll without slip. Okay, so if I do the substitutions, and then we had assumed alpha of the disk was some minus alpha disk in the k direction, and then we know that the position vector from point C to point G is going to be pointing in the negative en direction. Okay, so if this is point C, if this is point G, then the arrow is going to point from C to G, so this is going to be r of G slash C. Okay, I'm going to write the G carefully, r of G slash C. Okay, so if you do the substitutions, you'll end up getting the same expression. I just want to show it very quickly. So r plus r theta double dot et minus r plus r theta dot square en. This is the acceleration of g, is acceleration of c. Then I'm going to have minus alpha disk in the k hat direction crossed with this is alpha disk in the k hat direction crossed with a minus r en, and then lastly I'm going to have minus omega square of the disk times minus r en. Okay, so this is the normal component, and so if I take all the tangential unit vector components on both sides, I'm going to have r plus r theta double dot on the left hand side, and then if you do the cross products using the triads, you'll find out that this is going to be alpha of the disk times r. Okay, so this essentially tells me that alpha of the disk is the same as what we had obtained from before. And if you want, you get an additional piece of information which tells you that minus r plus r theta dot square in the normal direction is going to be acceleration of the point C in the normal direction. Okay, and then I'm going to have minus and minus, so that's going to be plus r times omega disk square. So the acceleration of c in the normal direction, which I'm calling this way, can also be obtained. Okay, not interested in it, I mean not our interest, but you can find it. So this is the same as before, this alpha here. So there are two ways to do this. One is by making use of differentiation, because I know omega is a function of time, alpha is just rate of change of omega. The other is by using vectors. Okay, so at the end of the day, what do I have? Acceleration of g with respect to fixed observer is r plus r theta double dot in the tangential direction. And I'm sorry, this has to be a positive sign. So this is a positive sign here. Apologies for that. This was supposed to be a positive sign because it's in a normal direction, right? Circular motion. Okay. And other than that, it's fine. Anyway, it's not of interest to us. And this is r plus r theta dot square in the normal direction. Then I obtain alpha of the disk is going to be minus alpha disk in the k hat direction. I had assumed it to be clockwise. I obtain alpha disk to be positive, so my assumption of it being clockwise is still correct. So this is going to be minus r plus r theta double dot divided by r in the k direction. Okay, and I want to make a note. Since we obtained alpha disk to be positive, our assumption of alpha disk being clockwise is correct if the disk is traveling the way it is as shown in the previous figure. Okay, so these are the things that we actually need, because this is the end of the kinematics part of the problem. Now we go to the kinetics part of the problem, which is fairly straightforward. We just have to draw the free body and the kinetic diagram. Okay, so the kinetics of the problem. Okay, since the body is rolling without slip, there is the static friction at the contact point between the disk and the track. Okay, so that's one thing that you want to know. Then what are the free body and kinetic diagram forces and so on. I'm just going to bring the figure that I have from before here. I'm assuming this is the, maybe I do have it. Sorry to keep going up and down, but I just want to see if I have the figure from before. Yeah, fantastic, I have the figure from before. I'm going to get rid of many of these things, okay, so because I'm drawing the free body and the kinetic diagram at some arbitrary point in time, I don't even need this entire thing. I'm going to get rid of that point C, let it be there. I'll get rid of that. The directions are fine. The D point is a point on the disk. I'm going to get rid of all of these creatures, cut that off. This is theta of t at some arbitrary point in time. I can keep that. So when I draw the free body diagram, I need to be careful. Okay, so this is the center of mass. This is the point C, which I'm going to draw here. Okay, and for the sake of simplicity, I'm just going to take my normal and tangential directions and then draw them out here. Okay, so it's kind of understood that this tracks the normal and the tangential directions. Okay, so I'm going to draw the forces acting on it, and then I'm going to draw the kinetic diagram as well. I actually do not need most of these. Okay, so I'm going to get rid of all of that and let this be there, because this is where the track was contacting. So this was the point O, which was sitting somewhere here. I actually don't need to show it, but just for the sake of reference, I'm going to show it. So I'm going to copy this and I'm going to paste this. I'm going to have my kinetic diagram here. Okay, so this is my free body diagram. This is going to be my kinetic diagram. Okay, so on the free body diagram, what are the forces? First of all, I'm going to have the force of static friction. Okay, so the force of static friction is going to be pointing in this particular direction that I'm drawing. Okay, I would like you to think why it is pointing this way. Okay, so this is F mu static. And one way to think of it is you want to see what is the direction of rolling of the disk. The disk is rolling clockwise, which means that if I sum moments about the center of mass of the disk, the only force that is providing a clockwise torque is the static friction force. So the static friction force has to be pointing this way. Then I'm going to have a normal force between the track and the disk. So this is the normal force. Then I'm going to have the weight of the body, which is acting vertically down. Okay, so this is going to be mg. And I know that from here to there was the angle theta of t, which means that I can break the force mg into components parallel and perpendicular to the tangential direction. So this angle is also theta. Okay, so that's also theta here. I'm going to draw that out here. So this is theta. So this is going to be mg times cosine theta. And then the other component that is going to be in the tangential direction is going to be mg times sine. Okay, and the distance from point G to point C is the distance little r. This is the force free body diagram, nothing else going on. The kinetic diagram, important things going on in the kinetic diagram. Okay, what are the things? First of all, I have to mark the direction of the acceleration. Okay, so there's going to be two inertial forces. So this is going to be m times at, m times an. Okay, and this is the at and an are the acceleration of the center of mass. Okay, so a g slash o is going to be at, et, an, en, where your at is r plus r, theta double dot, and an is r plus r, theta dot square. Then one more thing I have is the inertial torque. Okay, so this inertial torque is going to be marked in the same direction as the rotation. Okay, and this guy is going to be ig times alpha disk, or ig times r plus r divided by r theta double dot. Okay, so this is because we know alpha of the disk is r plus r divided by r times theta dot. So inertial torque is Ig times alpha of the disk. This is a couple moment. Okay, so this is the free body diagram, this is the kinetic diagram. Just going to copy these creatures one more time, okay, just so that I can write it out nicely down below. Okay, so I'm going to go to the next page, and hopefully I can paste it and we'll be done with this problem. All right, so these are the free body diagram and the kinetic diagram ideas. Now I want to obtain the equation of motion. Okay, so to obtain the equation of motion, my equation of motion cannot contain any constraints. Okay, so I'm going to write that down here. So equation of motion cannot contain any constraints. Okay, so which means that the equation of motion should not contain pin reactions, normal force, tension. Okay, that's one thing. Then static friction. Okay, so these are things that it cannot contain. And this is because, you know, if I'm what I'm trying to do is I'm trying to I'll once I obtain the equation of motion, which is going to be a second order ordinary differential equation, I solve for the dependent variable to obtain the system response, right, how the system moves. But if my equation of motion contains the constraints, then how would I solve for the system's solution without knowing what the constraints are, without solving for the constraints? So I cannot solve for the constraints beforehand because I don't know what the system is doing. So if the equation of motion contains the constraints, I'm in a complete bind, right? Because I can't do anything. So which is why the equation of motion should be bereft of any constraints. Okay, reactions or moments or forces, either of that. Okay, so I go here, which means that my idea is, you know, I don't want to sum forces. If I sum forces up, then I see that the constraints will come into play. In the free body and kinetic diagram, the constraints will come into play. Okay, so this essentially means that we do not want to do that in this problem. Okay, so once again, this is for this particular problem. Okay, if you sum the forces, you will see that the friction force and a normal force might come into play. So I don't want to do that. So I want to sum moments. Which point do I sum moments about? I'll sum moments about the contact point, see, because if I do that, then I get rid of all the constraints. Okay, so I'll sum moments about C on the free body and the kinetic diagram, so that all the constraints, which is the static friction force and the normal force, do not come into play. Once again, if you have rolling without slip, the force of friction is the static friction force. If you have rolling with slip, then the force of friction is the kinetic friction force. This becomes a multi-degree of freedom system because I'm going to have no relationship between the translation of the center of mass and its rotational rate. Okay, so that's not the problem I'm trying to solve here. Okay, this is a problem with rolling without slip. Okay, so this is the static friction force. It's a constraint. Why is it a constraint? Is because the static friction force will have a value less than or equal to the coefficient of static friction times the normal force. So this is an inequality. It's not an equality. So I have no idea absolutely what value of F mu s is at any given instant in time. All I need to know is it has to be less than mu s times n, which is the static friction coefficient times the normal force. Okay, so if I do the sum of moments, and I'm going to bring this figure once again down below. Okay, I'm going to copy, I guess I want to copy the entire thing. Okay, sorry about that. I'm going to copy the free body and the kinetic diagrams, and then I sum moments, and then I'm almost done with this problem. Okay, so I'll come here, paste it here. So sum of moments about the point C. So that's my statement here. Sum of moments about the point C on the free body diagram is equal to sum of moments about the point C on the kinetic diagram. I'm going to assume that counterclockwise rotations are treated as positive. Okay. It does not matter what you choose as positive or negative as long as you're consistent. If I sum moments about the point C, you'll see that I'm going to have minus mg times sine theta times the distance of r. That's the only moment due to the forces on the free body diagram. This is going to be, first of all, inertial torque minus ig times alpha. And then I'm going to have a moment due to mat as well. Okay, so watch that out. So this is going to be minus m times at times the distance r, right? So this is the distance little r. Man does not cause a rotation about point C because it has a line of action passing through the point C. Okay, do the substitutions. So this essentially tells me minus mg times r times sine theta is minus ig, which is half times m times r square. Alpha of the disk is r plus r divided by r times theta double dot, minus m times r plus r times theta double dot, which is the tangential acceleration component, and multiplied by the radius r. Okay, I can cancel off the radius r everywhere, so you can see this is gone with that, then this creature is gone, so this is gone, then that is gone, and then that is also gone. Okay, so I'm now going to combine things. So minus mg, and I can cancel the mass also off everywhere, so let me do that too. So this is gone, this is gone, this is also gone. Combine the like-minded terms. So I'm going to have minus g times sine theta. This is going to be minus half, and I can get rid of the negative signs, make everything positive as well. Later on I'll do that. This is r plus r theta double dot minus r plus r theta double dot. Get rid of all the negative signs, make them all positive. So this tells me that 3 by 2 r plus r theta double dot is equal to g sine theta. Okay, or if I write the equation of motion properly, so this is going to be theta double dot, and then I'm going to bring this as minus g sine theta, and I'm going to have the factor of 2 by 3 times r plus r is equal to 0, or write it more nicely, theta double dot minus 2g by 3 times r plus r. So this creature has to be in the denominator, so this is 1 by r plus r, and this is going to be sine theta is equal to 0. Okay, so this is the equation of motion. Equation of motion does not contain any of the constraint forces. Okay, and typically, this equation of motion will reduce to that of a simple pendulum, an inverted simple pendulum. Okay, so this can reduce to the equation of motion of an inverted pendulum. Of course, the length scales will be different, okay, but this is in general the equation of motion of an inverted pendulum is going to be similar to what you see here. Okay, so the equation of motion of an inverted pendulum inverted pendulum meaning that if this is the pendulum string and this is the pivot point and here is the pendulum, this is the inverted pendulum of length L. If I say that theta of t is the degree of freedom associated with it, the equation of motion is theta double dot minus g by L sine theta is equal to 0. Okay, or if you have so you can see that by comparing this equation with that equation, I'm just off by a small length scale. Okay, 2 by 3 r plus r is equal to the length 1 by L. But other than that, this can be reduced to the equation of the inverted pendulum by factoring in the length scale. Okay, So this is essentially the end of the problem. I would hope that this serves to act as a good review of fundamental dynamics that we need for this particular course, ME 3260. And I'll be more than happy to clarify any questions if you have them on. All right. Thank you for your time. This is what we wanted to achieve, we set out to achieve, and we have achieved it in this particular problem. Thank you and take care.